Hello, this is Mr. Anderson for Keller Community College with part 2 of section 4 of chapter 7. We're going to be where we were dividing rational expressions, but in this part we're going to be rationalizing denominators. The denominators in these problems are all square roots or other form of roots. Now, these roots that cannot be simplified are all irrational, and dividing a number by an irrational number is not really good for us. So what we're going to do is spend some time to rationalize these denominators by fixing them in a way. Now, there are different techniques for different roots, but the one that I always follow is this one-size-fits-all form where we are going to multiply by 1 so that the denominator makes a rootable number or variable. So, let's take a look at this. The square root of 7/2. Now, if we just divided that, it would be 3.5, and if we took the square root of that, it would be a decimal. Our job is to not get any decimals, not have our square roots in the denominator. So if I break this up into the square root of 7 divided by the square root of 2, you'll notice that I have this in the denominator. So I think to myself, what is a number that 2 can make that can be square rootable? See, for our x squares, we have, or any number that's squared, 1, 4, 9, 16, so on and so forth, I'm going to try to find a number that 2 can make into one of these numbers. And the number that 2 can make into one of these 4 numbers here is 4. So if I multiply by 1, which I will draw as a giant rectangle representing my 1, I'm going to multiply by square root of 2 over square root of 2. This gives me the square root of 14 over the square root of 4. And 4 is a rootable number. The square root of 4 is 2. So that my final answer, without having a square root in the denominator, is square root of 14 over 2. You will notice that I've changed the problem from this to this, but if you test this on a calculator, try doing the square root of 7/2 or 3.5. You will find it's equivalent to this, but this is just good mathematical punctuation to not have a square root or any kind of root in the denominator. In problem number 12, only focus on the root that's in the denominator. Do not focus on the number in front of it. If I extend my chart here a little bit to 25, 36, and 49, the square root of 7 can be multiplied by the square root of 7 to make 49. I will now multiply the top and bottom by the square root of 7, which is in essence like multiplying by 1. So now I have 3 times the square root of 35 over 2 times the square root of 49. The 5 times 7 made 35, the 7 times 7 made 49. So now I have 3 square root of 35 over 2 times 7, which makes a total of 3 times the square root of 35, and 2 times 7, which is 14. And there's your answer there. Now we have no square roots in the denominator, and we have a problem that's equivalent to what we have over here. Now when we get to the cubic root, it probably would help having some cubic rootable numbers here. So 1, 8, 27, 64, 125, and 216. So what this does is we need to look at the numerator, which is the cubic root of 2, and the denominator, which is the cubic root of 9, and think to ourselves, what can I make this denominator into one of these numbers listed on my chart? And the easiest one to take 9 and make into one of these is the 27. So I'm going to multiply the denominator and the numerator by the same thing, thus keeping it the same, but changing its appearance only. So this is going to be multiplying by 3 here, multiplying by 3 here. Cubic root of 2 times the cubic root of 3 is the cubic root of 6, and the cubic root of 9 times the cubic root of 3 is cubic root of 27. And what we'll do is simplify that fraction, or simplify that denominator here, because the cubic root of 27 is 3, and the numerator is going to be still the cubic root of 6, since 6 cannot be changed at all. Problem 14 and problem 13 are very similar. You'll notice that we're still dealing with cubic roots. So what I'm going to be doing is multiplying the top and bottom by a cubic. However, you'll notice that the bottom has a y in it. And things change a little bit when we go to variables. Because even though to get to a 27, I'm going to multiply the bottom by 9 and the top by 9 under the cubic root, I need to get this to be y cubed. Because as we learned earlier, if you take the nth root of any variable to the nth power, that is going to be just the variable itself. So how many y's will I need to make this equal to the index? Well, I would need 2, because y squared raised to the y power is going to be y cubed, and that will give me my denominator that I need. My numerator is going to go 9 times 7, which is 63, and xy squared. The numerator can no longer be simplified. Now my denominator here is going to be the cubic root of 3 times 9, which is 27, and y times y squared, which is y cubed. Therefore, my numerator is the cubic root of 63xy squared, and I have the cubic root of 27, which is 3, and y cubed, which is y. Y cubed under the cubic root is just y. Alright, it might be handy to actually leave these root charts somewhere on your worksheet so you can refer to them later. Let's go and take a look at some more problems down below here. Alright, now taking a look at problem 15. Problem 15 has some x's and y's, but we really need to focus on the denominator. So I'm going to multiply top and bottom by some cubic root so I can get my 2 to simplify. Now, in my cubic root chart, 2 times 4 will give me an 8, and the cubic root of 8 is 2. Now, here's the thing. 3 can go into 7 2 times, but I'd really want this 3 to go into a y value that's even, or that will divide evenly. So I'm going to multiply by y squared. So this in the numerator is the cubic root of 4y squared. So that what I get in my denominator is going to be the cubic root of 8 y to the 9th. That way I can take the cubic root of 8 and 3 goes into 9 evenly. Now my numerator is going to change a little bit here because I'm multiplying by 4y squared, so 3 times 4 is 12, and x to the 4th y squared. Now let's take a look at simplifying the denominator. My denominator, the cubic root of 8, is 2. Then the cubic root of y cubed, or how many times does 3 go into y to the 9th, is 3. Now my numerator is going to be this piece, but some of you might have noticed that x to the 4th is bigger than the cubic root. So I can pull out an x, because 3 goes into 4 once, with 1 left over. And that leaves me with the cubic root of the x that's, or the 12, excuse me, I forgot the 12 right there, the 12, the x, and the y squared. It is important to note that the 12 and the 2 cannot be simplified because one's inside the cubic root and the other is not. In problem number 16, we're going to just focus on the denominator variables. So my question to you is this: what do I need to multiply my denominator by to get perfect rootable numbers out of those fractions? So the x would have to get multiplied by x squared to raise it to x cubed, and the y would have to get multiplied by y squared to make it y cubed. So the numerator and denominator both get multiplied by x squared y. So this leaves us with, in the numerator, the cubic root of 5x squared y, and the denominator is going to be the cubic root of x cubed y cubed, which can be simplified in the denominator to xy. And the numerator stays at 5x squared y. problem number 17, you have to think to yourself, what would I multiply 20 by to make it a rootable number? Now, the smallest rootable number of 20 and 5 would make 100. You're looking for the smallest rootable number in your chart, and 20 times the square root of 20 times the square root of 5 is the square root of 100. This also means that your numerator is going to be the square root of 15x, because 5 times 3 is 15. This gives you 15x over 10. And there's your answer. Problem number 18, we are going to take a look at getting the fifth root worked out here. Now what's kind of handy is that if you check and try to think about, let's see, 32 is perfectly rootable by 5. So when we multiply, we won't need to change the 32 because the fifth root of 32 is 2. But we do need a couple more x's and y's, 3 x's to be in particular, and 4 y's, because that will give us our x to the 5th and y to the 5th. Okay, so here's what we have for our top. Our numerator is going to be the 5th root of 9x cubed, y to the 4th. And our denominator is going to be the cubic root. Now I'm going to save a little time here and write down kind of my little scrap work here. Here's our 5th root. So the 5th root of 32 is 2. The 5th root of x to the 5th is x, and the 5th root of y to the 5th is y. So now we have our denominator rationalized, we have no decimals, and we also used our root chart. Looking down at problem number 19, gives me a little more room there, not too much, but every little bit helps. We have to look at the fourth power. Now, when we look at our powers of 4, 1 to the 4th power is going to be 1. 2 to the 4th power is 2, 4, 8, 16. 3 to the 4th power is 81. And 4 to the 4th power is 256. So what this means is that this 64 in the bottom isn't actually one of these 4 numbers. So what I'm going to do is I'm going to modify that 64 by multiplying the 64 by 4 to make 256. To make my x squared into something that can get rootable from the fourth degree there, or the fourth index, this is going to be x squared, because that will make, when I combine it with the other x squared, x to the 4th under the 4th root. Now, the last part, since our y to the 4th is all set, we don't need to do anything to that. So my numerator is going to be 28 x squared all over and again, I'm going to kind of shorten this up here a little bit by taking 256 x to the 4th, y to the 4th, all under the 4th root. So the 4th root of 256 is 4, the 4th root of x to the 4 is x, and the 4th root of y to the 4 is y. And for our last problem here, the easiest way to do it is to see and examine it, because you might actually get away with doing the problem without actually having to rationalize the denominator. Because 21 over 75 is reducible if you divide the top and bottom by 3, because this is a reducible fraction. So what we have is 7 over 25. Then x over x, if you do your power rules, 2 minus 1 leaves me with x, and 1 minus 5 is negative 4, or leaves 4 in the denominator. Now my numerator and denominator get square rooted independently, and my numerator is the square root of 7x, and my denominator, perfectly rootable. This is 5, because the square root of 25 is 5, and the square root of y to the 4th, or how many times does 2 fit into y to the 4th? It fits in twice. Well, thanks for watching.